Okay, so this gets recorded, so that will be shared with everybody afterwards. So let me get started with this makeup class. This is the last lecture of this semester. And let me share screen. I prepared slides. Can you see the slide? Drew, Sarah?
Yeah, I can see the
Yes.
slides.
Okay, and in one slide or two slides?
I see one slide.
Okay,
Just one
that,
slide.
that- okay, good. That's the way it's supposed to be. Okay, so to wrap up the course on non-perturbative aspects of beyond standard model physics, I'd like to talk about the research I've been doing lately, last several years, how to use supersymmetry to solve QCD. And just to recap, the non-perturbative gauge theories is a very important because it's really central part of QCD. We'll review that. So chiral symmetry breaking, absence of free quarks. So we loosely call this confinement, but as we discussed in class, there's no rigorous notion of confinement in QCD because the quarks are in the fundamental representation. But nonetheless, we don't see any free quarks. That's also a non-perturbative aspect of QCD. We talked about U1 problem, namely that at the classical level in the Lagrangian, there is a U1 flavor symmetry, which appears to be spontaneously broken, but there's no apparent corresponding Navier-Goldstone boson. Then eta prime is a particle which is a candidate for that, but it's heavy. And the reason why this heavy is, again, non-perturbative effects, namely that this U1 symmetry is anomalous in QCD, and that normally ends up giving this mass to eta prime. Exactly how is, again, non-perturbative issues. And theta parameter is a surface term in QC Lagrangian. So in perturbation theory, it doesn't do anything, doesn't give you any Feynman vertex or anything like that. But nonetheless, it is believed to be physical. And that's why we talked about axion. So if theta parameter is physical, that would induce the neutron electric dipole moment, which is against the experimental limits. So that's why we wanted to solve that problem by introducing an axion. So this whole aspect is non-perturbative. So we can't see any of these things in perturbation theory. That's why we focus so much on non-perturbative aspects of QCD this semester. And Lattice QCD, of course, is amazing. They can do a lot of quantitative calculations, including these non-perturbative effects. But it's a kind of black box. It's difficult to get insight into what exactly is going on in the theory. So that's why we try to think of something else to do. And in particular, when you move away from QCD and think about chiral gauge theories, right now there's basically no tools to analyze these theories at all. So having a definite methodology would be, of course, very, very welcome. And so the main point I'd like to convey in the lecture today is the following. So oh, I'm sorry, I went back in slide. The main point I'd like to convey in the lecture today is the following. So there are very few methods to study strongly coupled systems, including these non-perturbative nature in QCD, which are essential to understand some of these most important aspects of the strong interaction. So the idea is that supersymmetry makes exact analytic studies of non-perturbative effects. So that's actually a wonderful tool to study non-perturbative effects. And then you have to break supersymmetry and in a particular way. So what I will tell you today is that we use this idea called the anomaly-mediated supersymmetry breaking. And if you take this particular way of breaking supersymmetry, then it still allows for exact solutions inheriting from this exact supersymmetry limit. So namely, that idea here is that we are trying to study a cow, and but that's very difficult. We can solve the cow problem. So we have to simplify it. So first we make it supersymmetric. So that's a spherical cow. But spherical cow doesn't resemble the real cow at all. It's too symmetric. And that is the supersymmetric limit of gauge theories. The point here is the minute you actually introduce a small breaking of supersymmetry in the specific way I mentioned earlier, then you can start picking up, where the head is, where the tail is, and all the features of the real cow already at this stage of small supersymmetry breaking. And that's the way we try to extract information about the non-perturbative effects in non-supersymmetric gauge theory. So that's the idea. And using this method, I have been able to work out many different aspects of non-perturbative effects in QCD. We can actually derive, even on a piece of paper, that the chiral symmetry is dynamically broken. We can also show the confinement happens. And so to really show confinement in a rigorous way, we have to go to theories where the quarks are not in the fundamental representation. So I will go to SON gauge theories instead of SUN gauge theories later on. But there you can really identify magnetic monopoles in the spectrum and show that they actually acquire expectation values leading to this confined flux tube for the color electric field. So that's the way we can understand confinement too. For the U1 problem, I can actually work out what the mass of the eta prime is, and then show it's actually heavy. And we have to define what we mean by heavy, and that will come up later. The chiral Lagrangian is also not a jump from the UV theory of the gauge theory to IR theory of the mesons. This is something we can derive from the original UV theory, and so that's something we can work out. And it comes with this idea called hidden local symmetry, which is supposed to be sort of the principle behind the chiral Lagrangian. I will tell you what that is in a moment. And also it comes correctly with the Westermino-Witten term we really need to understand the aspects of anomalies in chiral Lagrangian. So again, that's not something you add by hand, but something that just comes out from the theory. And we didn't talk much about it, but in QCD, the TOEF started this business of talking about large NC limit. And NC in QCD is 3, so it may not appear large, but it does actually show many features of the QCD as an power series expansion in 1 over NC. It's not that that provides you any exact solutions or anything, but it just gives you a useful way of looking at diagrams and see what's important, what's not important. In particular, in the limit of large NC, the prediction is that the pion decay constant squared has to be order NC. And that's something we can also work out and show that that is the case. And there are also non-perturbative condensates in QCD, like QQ bar condensate. We talked a lot about this in the context of chiral symmetry breaking. We didn't talk much about this gluon condensate, but that is also known to exist in QCD. And once again, these things cannot be computed in perturbation theory. They are inherently non-perturbative objects, but using the technique I just briefly mentioned so far, we can actually work them out too. And Witten came up with this very strange formula to relate the mass of the eta prime to what is called topological susceptibility, and which is topological susceptibility is the idea that the energy of the ground state depends on theta. And so that theta is actually a physical observable that way. And so this is the second derivative of the energy with respect to theta parameter. And so eta prime mass squared and this quantity are actually related. And so within this technique, we can work out both of them and show indeed that they're related, at least in the large NC limit. That's where Witten made this prediction on. We can also work out the spectrum of the hadrons, which are parity even and spin 0 at the low end of the spectrum. And this has interesting history behind it. I will come back and talk briefly about it. But nonetheless, this is something we can work out too. And also, when you move to chiral gauge theories, we have very little idea on what they actually do. So using this technique, we can also show what kind of global symmetry is dynamically broken in the ground state in these chiral gauge theories. So that's can be worked out as well. And especially those things I colored, they are not possible, or at least very difficult to study, even using that as QCD. So it's not only that we can reproduce many of these non-perturbative features, we can also do something no other methods can actually do. So that's sort of the sales pitch of what I'm going to talk about today. So just a brief recap of our QCD. We did go through this at the very beginning of this semester. So QCD is difficult and nobody has been able to really quote unquote solve QCD. So when we first learn about quarks, we get told that we can actually never see them. So I already mentioned that it sounds like an internet scam of some sort. I just happen to still have some of the internet scams in my inbox. So here's one of them. If I send them my information, they promise to send me money. Of course, they would never do. So that is how it felt like when I first heard about it. Then you get told that, well, you don't see quarks because, there's something called confinement. You can never liberate them. And indeed, QCD coupling constant becomes very strong at the low energies with the property called asymptotic freedom, and because the negative Weyl function. But having the theory going strong doesn't necessarily mean that theory does confine. For example, we already now know many examples of strongly coupled gauge theories which don't confine, but lead to an infrared fixed point and become a conformal field theory. So strong coupling, growing beta function does not necessarily mean confinement. So this is still only suggestive. And we talked about another puzzle in QCD, that the protons and pions are made of the same quarks, up and down quarks, but their masses are very, very different from each other. And that's mysterious. And this mass difference already, we talked about this, is very important to understand the entire chemistry and therefore our existence in the universe. So looking at the spectrum of the particles in QCD, the proton and neutron are up there, here's the pion, and they're made of the same things. So there is this big disparity between masses. And so that's the question. And the reason why that's an important question is because the pion, as Yukawa told us, is the particle that mediates the binding force within the nuclei among protons and neutrons. So if the pions are heavy, then its Compton wavelength is short. So when you exchange pion, the pion coming from one proton inside the nucleus cannot even reach the neighboring neutron to bind them together. So nuclei wouldn't bind. But if the pion is light enough, then they can go over distance so that you can connect the proton inside the nucleus to neighboring neutron or another proton and bind them together. So that's how nuclei are actually bound. So if the pion is not light enough, as we know from experiment, then none of these nuclei can actually exist in a bound system, so that all nuclei would disintegrate into just hydrogen and neutron, the protons and neutrons. So there will be only hydrogen as an element in the entire universe. So certainly we cannot live in that kind of a universe at all. So that's why we would like to understand these things better. And there's some qualitative picture that can make us feel better. And I already mentioned this. Our late colleague, Stanley Mandelstam, came up with this quote-unquote explanation on how confinement might work based on this idea called dual Meissner effect. So the Meissner effect in superconductivity, which we can study in the laboratory, is that the magnetic field, it can be squeezed into a tube we call flux tube, and the energy of the flux tube is constant per length. So the total energy is proportional to the length. So if we have a solenoid on one end, another solenoid on the other hand, the total energy of the magnetic field inside a superconductor is proportional to the distance between the north pole and south pole of the solenoids. So there is a linear potential between two solenoids. So what Stanley suggested is to switch electric and magnetic in this picture. So in the usual superconductor, what we know is that the Cooper pair of electron is what condenses to make the system superconducting. And electron, of course, is an electric object. So electric object, when it condenses, would squeeze the magnetic field into flux tubes. Then if you switch the electric and magnetic, if you have a system where magnetic object is condensed, such as magnetic monopoles, then the electric field would be squeezed into flux tubes and to produce a linear potential between two electrical sources. So quark has a color electric charge, antiquark has an anti-color electric charge. So there's supposed to be color electric field in between, but in the presence of this condensate of the magnetic monopole, the color electric field is squeezed into flux tubes, and therefore the potential between quark and antiquark become linear in distance, and that's the idea of confinement. So that sounds very nice, but you should still ask the question, okay, is this really happening in QCD when we actually don't know what magnetic monopole actually is within QCD? And not even to mention, we need to even understand why that actually condenses in the ground state. So this is a nice picture, but it's not clear if this is really what's happening in QCD. And same is chiral symmetry breaking. So massless QCD, we talked about this, is invariant under this flavor symmetry of rotating NF flavors of the left-handed quarks, rotating NF flavors of the right-handed quarks. They also use a baryon global symmetry. And we assume that this is broken to the diagonal subgroup SUNF vector to rotate the left-handed and right-handed quarks in the same way, because there is a condensate of this quark bilinear operator. So if you accept this picture, then there's a general theorem that tells you that there are massless Navier-Goldstone bosons when we identify them with pions and kaons. And of course, in the real QCD, the quarks are not massless. They have a small but finite masses. So this symmetry is explicitly broken. So by combining this spontaneously breaking and explicit breaking, pion would acquire small but finite mass, but it still remains light, because in the limit of the quark mass going to zero, pion is supposed to become massless. So this is a nice picture to explain why pions are light. But once again, we have to make this postulate that the chiral symmetry is spontaneously broken in the QCD vacuum. So neither of them are derived from QCD. So the reason I'm talking about supersymmetry today is not for the purpose of solving the naturalness we talked about for the electroweak symmetry breaking, but really as a mathematical tool so that we can solve and understand these non-perturbative aspects of gauge theories, which go back to the famous work by Seiberg and Witten. So what they did is to take a really spherical cow, which is an SU2 gauge theory, which has two sets of supersymmetries. So that's a very spherical, highly symmetric system. And that's why there's so many constraints that they actually managed to solve this theory exactly. So in this theory, if you look at the particle spectrum, there is a scalar field, which is a triplet under the SU2 gauge group. And they tend to acquire an expectation value without costing any energies. So it turns out that there's an infinite set of ground states in this theory. Each point in this infinite the ground states is actually a vacuum with expectation value for the triplet that breaks SU2 gauge theory to U1. And according to 't Hooft and Polyakov, when SU2 gauge theory breaks to U1, you can solve the field equation and find actually magnetic monopoles as a solution to the field equation. So the magnetic monopoles do exist in this theory. And among the infinite number of the ground states, there are special points. And what is amazing about Seiberg-Witten work is that they could convincingly show that at these special points, the monopole or dion is a magnetic monopole, which also has electric charge, and these objects become massless. And we started with this highly, highly spherical cow. We go to a slightly less spherical cow now by breaking two sets of supersymmetries to only one set. And by doing so, they could demonstrate that these magnetic monopoles do acquire expectation values and hence cause confinement a la Stanley Mandelstam. So that was an amazing piece of work. But it doesn't quite satisfy our needs because here you don't have any matter fields. It's all gauge multiplet. In order to talk about chiral symmetry breaking, you need to bring in matter fields. But because this n equal 2 theory is really highly spherical cow, it turns out that it doesn't have chiral symmetry to speak of. So it actually doesn't help us to understand the mechanism of chiral symmetry breaking. So instead of having this very, very highly spherical cow, we go to a normal spherical cow, which has only one set of supersymmetries, and that is actually a work done by in a series of works by Natty Seiberg. And he actually managed to solve these theories too, which is also amazing. But it turns out that his solutions don't look like QCD at all. The phase structure is just way too unusual compared to what we expect to what happens in QCD. So this is the brief summary of what Seiberg told us. So m equals 0 in my notation means this is the supersymmetric limit. So that's a spherical cow. And let's say we talk about SUN gauge theories, SUNC, NC being number of colors. And the dynamics of theory depends sensitively on the number of quark flavors you have in this theory. And when the number of flavors is NC minus 1 or less, it turns out that theory even doesn't have a ground state, and it has a behavior called runaway behavior. And I will come back and talk about this in a moment. So that certainly doesn't look like QCD at all. If you have exactly the same number of flavors as number of colors, it turns out that there's now infinite number of ground states instead of a single ground state. In vast majority of them, you end up breaking baryon number symmetry. Again, that's not what you would expect in QCD. When you go to one higher number of flavors, then the theory does seem to confine, loosely speaking, but there's no color symmetry breaking. Again, that's not what we expect in QCD either. And if you go to higher number of flavors, you find something even more bizarre in this theory. So if the gauge theory becomes strong, the cores seem to get combined into baryons, but those baryons fragments into different smaller pieces, and those smaller pieces now behave as a free quarks under a different gauge group from what you started out with. So you end up with a free magnetic theory, so-called, which is a theory which is asymptotically non-free. The gauge theory is weak, and the quarks now transform under this different gauge group from the original SUN. Again, that's very difficult to intuitively understand. And if you go to even higher number of flavors, you get the IR fixed point. And beyond 3NC, the theory is no longer asymptotically free. So that is the result by Natty Seiberg. Now, what do we know about non-supersymmetric QCD? It's actually rather little. So if you go above 11.5 NC, then theory is asymptotically non-free. So in the infrared limit, theory basically becomes free quarks. So that part, is easy to understand. And if you go just a notch below this boundary, then you can find the IR fixed points too. So in this case, something called Banks-Sachs fixed point can be shown to exist. And in the limit when NC is large, you can show the beta function is something of this order, g to the 4th times order 1 minus g to the 6th times order NC. Then you can find the fixed point where beta function vanishes when g squared is order 1 of NC, which can be weak enough when NC is large. So you can demonstrate that there is indeed an inverse fixed point for a small coupling where you can trust this perturbative expression in the beta function. So this fixed point does exist, at least in the large NC limit. But if you go order 1 below this point, then you completely lose your control, theoretically, to work out the infinite fixed point. Now, for small number of flavors like 2 or 3, we talked about chirosymmetry breaking, which we learned basically from experiments, not from theory. And the lattice QCD results are consistent with this idea, but again, it's not easy to understand how this actually comes about. And in between, we don't really know. So it is normally believed that chirosymmetry breaking would persist to a much larger number of flavors, and then it switches over to infrared fixed point. But where that happens, if there's anything in between, we don't really know. So the end result of my lecture today is the following. So starting from the spherical cow, we introduce small supersymmetry breaking. So now it starts looking like a real cow. And I can show that for the smaller number of flavors, the global minimum is really the ground state that would break chirosymmetry. If you go to larger number of flavors, unfortunately, chiral symmetry breaking is not the global minimum. It's a local minimum, but at least well-defined. And so the idea is that when you think about how theory would behave, when you start with a small supersymmetry breaking and slowly jack it up and go to a limit where supersymmetry is very badly broken, and therefore it's basically non-supersymmetric QCD, then you have to cross this barrier where the size of supersymmetry breaking becomes as large as the QCD scale. And some people speculated that there's a phase transition at this point, so that what you learn for small SUSY breaking does not tell you anything useful about the large supersymmetry breaking. But from what I could see by studying this in great detail, it does seem to be that they are continuously connected. At least I don't see any sign of the phase transition. So if you buy into that idea, what we learn about non-perturbative physics for small SUSY breaking would carry over to the large supersymmetry breaking and hence non-supersymmetric real-world QCD at the end of the day. So we are getting insight into that. For a large number of flavors, I told you that the chiral symmetry breaking is a local minimum, but I can follow through how this local minimum is continuously connected to the non-SUSY limit. And again, I don't see any difficulty in doing so. So what is happening here is that there's a deeper minimum, which is not the standard chiral symmetry breaking, and that gets taken over by this local minimum once the SUSY breaking becomes larger than the strong scale. So this well-defined local minimum seems to persist continuously to non-SUSY limit. So once again, you can learn something near SUSY to the physics non-SUSY. So that's the idea. So to learn about the cow in a non-SUSY limit, I said we first go to this spherical cow that doesn't resemble the real world at all, like not having a ground state even. But the minute you actually break supersymmetry a tiny bit, you can really start picking up all the right features we expect in non-SUSY QCD. So that's the idea. And this point that the small parameter and large parameter may be continuously connected is something we have seen in atomic physics called the BCS-BEC crossover. So when you have a system of free fermions, we know what the ground state is. That's a gas of degenerate fermions, and that's the Fermi gas or Fermi liquid. So and that ground state does not break any symmetry in any way. But when you actually introduce a small attractive force among electrons, then what we know from the condensed matter physics is that the Cooper pair of electrons would condense and break the U1 symmetry. And that is the superconductivity indeed described by the Bardeen-Cooper-Schrieffer theory, BCS theory. So when you have a small attractive force, then this gas of electron would break the U1 symmetry. Now, once you actually start making this attractive force stronger and stronger, at some point, you lose your theoretical control. You don't know how to compute things. And when the coupling becomes very strong, then something non-perturbative would happen. Namely, electrons would form a bound state. And bound state is a boson. And that bound state boson can undergo a Bose-Einstein condensate. So in that limit, once again, U1 symmetry is broken because of the BEC. And so the idea is that as you change this small attractive force, make it bigger and bigger, theory becomes non-calculable and non-perturbative. But this idea of U1 symmetry breaking persists all the way continuously, and there's no phase transition between these two limits. So that is what it has been known in atomic physics and has been established both experimentally and theoretically. So what I'm talking about today is the similar idea seems to be working in QCD too. So here you have the SUSY limit. That's a Fermi gas, which is not interesting, doesn't break U1. But the minute you introduce tiny supersymmetry breaking, then it breaks chiral symmetry. And as you keep making the SUSY breaking scale bigger and bigger and becomes comparable to QCD scale, I lose theoretical control. I can't work anything out anymore. And if you go to large SUSY breaking, everything becomes non-perturbative and non-calculable. But here we believe the chiral symmetry is broken. And so from here to there, everything actually seems to be continuously connected without a phase transition. And that is a behavior called crossover. From one limit to another, you cross over without having a phase transition or discontinuity in between. So this kind of idea of starting with the supersymmetric gauge theory and slightly breaking it had been talked a lot about in the literature, especially in the 90s, and not much had been done more recently. And it turned out that, they had the right ideas, but many of things and effort have been abandoned for wrong reasons. But what we do is to build up on what people have done and focus on a particular way of breaking supersymmetry and push this idea much further what people have done. And so that this has now become a well-defined and usable technique to study non-perturbative gauge theories. And once you have this technique, you can apply this to chiral gauge theories and can obtain exact solutions there as well. Okay, so that's what I would like to talk about today. So let me stop here to see if you guys have any questions. Oh, now Rana and Ijun are there here too. Great, welcome. Any questions? No? Okay, if there isn't, then I just continue on.
Maybe we could go back
Okay.
to the mass of the pion slide.
Okay,
I
math Musabe Pion slide. Okay. Uh, what are you talking about? This picture here?
yeah, I guess this is the one that would explain the scale, yes.
Okay. So does that answer your question?
No, actually what I
Oh,
was gonna ask was, um, is it the case that the mass of the pion is like related to the short what I meant to say was the range
that's
of
right. That's
the
exactly right. Right.
strong
So
force.
if you compute the impact of exchanging pion between protons and neutrons in QFT, then that would produce Yukawa potential. And Yukawa potential is e to the minus mr over r. So 1 over
Mhm.
rp is the same as Coulomb potential, but you have this exponential damping behavior. And exponent is the mass of the pion times distance. So if the distance becomes bigger than 1 over mass of the pion, that's about 1 Fermi, then it gets exponentially damped. And there's basically no force beyond that distance. So
Mhm.
that is how you can define the range of the force given by inverse of the pion mass. So if you go to the distances above 1 Fermi, which is typically the case from one end of the nucleus to another end of the nucleus, they are separated by, say, 7, 8 Fermis. There's no direct interactions among them. So interactions are happening only among sort of the neighboring protons and neutrons, and that's how nuclei get bound. But if you go to a world where pion mass is, let's say, 3 times heavier, then the range of the force becomes a third of Fermi, and size of the proton itself is about 1 Fermi. So the pion exchange doesn't go even to the neighboring proton or neutron. And that's when the nuclei will stop binding anymore.
I
Does that
see.
answer the question?
Yes, yes.
Okay,
Thank you.
good. All right. Any other questions at this stage? Okay, so let me then continue on. And so here I have to introduce some formalism. And so if you get bored listening to formalism, you can fall asleep. And I can tell you when to wake up when we actually start applying supersymmetry to gauge theories. So the idea of supersymmetry is an extension of the Poincare symmetry we know and love about Minkowski space. So Minkowski space-time has 4 translation invariants and 6 Lorentz transformation, 3 rotations, and 3 Lorentz boost. So based on this principle of quantum field theory, there is now a theorem that says the only way to extend the Poincare symmetry with additional space-time symmetries is actually supersymmetry. And there's no other possibilities. that will give you a sensible S matrices of scattering amplitudes. So we know the algebra of the Poincare symmetry, so I don't write them. But here you have the generators, Q alpha, which is fermionic because they satisfy anti-commutation relations, and its index is a spinor index. So you have two spinors for left-handed spinor Q, and you have two spinor components for the right-handed or complex conjugate spinors Q bar. And based on the translation invariance and the Lorentz transformation property of a spinor, the first two are uniquely determined. And then for the consistency of the commutation relations, you can show that the only non-trivial anti-commutation relations are the following. Q's and Q bars anti-commute with each other, and Q bar anti-commutator is actually the Lorentz, space-time translation. So this is the unique extension of the Poincare symmetry to allow for some extra space-time symmetries. And once you have these algebra among the generators, you can immediately go to representation theory, what kind of mass spectrum or the particle spectrum you get. So by specializing to a massless particle, and choosing the direction of the momentum along z direction, if you put this into this QQ bar anti-commutator, you can rewrite it this way. So immediately you notice that in this case, Q2 and Q bar 2 are basically 0. But Q1 and Q bar 1 gives you a constant anti-commutator. So if you change the normalization, then Q and Q bar end up becoming annihilation and creation operator for a fermion like this one. And by combining also with this angular momentum operator in M, you can define the helicity of the particle. And you can show that the B would decrease helicity and B dagger would increase helicity by unit of 1/2. So that immediately tells you that you can have the following multiple structure. So out of this, the anti-commutator or creation annihilation operator, if you choose the ground state to have helicity minus 1/2, then, and so it's a ground state in the sense that it's annihilated by the annihilation operator. Acting creation operator would increase helicity by 1/2, so you end up with the helicity 0 state. Namely that you find a multiplet of a wire fermion, left-handed, because negative helicity, and a complex scalar with spin 0. So you find this super multiplet of spin 1/2 fermion and complex scalar particle. If you choose the ground state to be helicity 1/2, you can increase the helicity by d dagger to helicity 1, and helicity 1 has to be a gauge boson. So here you find a multiplet of the gauge boson, a partner with a spin 1/2 fermion, and that's a superpartner of gauge boson we talked about before, we call gaugino. I complained about the name, but anyway, this is how this gaugino and gauge boson multiplet comes about from this algebra of supersymmetry. And somehow I have the same slide once again, but here I was trying to explain what B dagger does to go from minus 1/2 to 0. And you can also have the complex conjugate multiplet, which includes the right-handed fermion and spin 0 particle. And then this is the gauge multiplet I mentioned earlier, which consists of the wire fermion and the gauge boson spin 1. So that's the multiple structure of supersymmetry, and CPT conjugate of that is down here. Now we would like to write the Lagrangian in the supersymmetric theory. And now here we do something very weird. So in addition to 4 spacetime coordinates, x, y, z, and t, we introduce fermionic spacetime coordinates, and which actually transforms as a spinor under Lorentz group. So this is a definition of superspace. In addition to 4 component of space-time positions, you have left-handed spinor with index alpha, right-handed spinor with index alpha dot, and together they form a space we call superspace. And quantum field is supposed to be a function of not only x, but also of theta and theta bar. And when you write down the field theory Lagrangian, this translation operator is always written as the derivative. And when you think about the Lorentz transformation, or rotation rather, then what you write is this derivative operator. So in quantum mechanics, this is xp minus xp, that gives you the orbital angular momentum, and that is a derivative operator. So in the same way, we would like to also write supersymmetry as a derivative operator. And roughly speaking, the supersymmetry is a translation in theta. But there's a little subtlety. So when you write down certain symmetry as a derivative operator, you need to make sure that your derivatives have certain properties that they commute or anti-commute among each other. So when you, for example, write down the gauge theory, you have the gauge transformation, and you introduce the covariant derivative to make sure that the derivative can be made consistently with the gauge invariance of the theory. So in the same way, when you write down your Lagrangian, that contains, of course, derivatives to give you the kinetic terms, derivatives should be written down in a way that is consistent with the supersymmetry transformation. Being consistent in this case is that the derivative operator should anti-commute with the supersymmetry operator. And so both of them are, roughly speaking, translation in theta, but by changing the sign of this additional piece that involves space-time derivative, you can make sure that QQ bar anticommutator really reproduces P, and Q and D anticommute with each other, and DD bar anticommutator is negative P mu, basically. And so using this, you can start writing down Lagrangian, or you can also constrain the superfields, which are a generic function of x theta and theta bar. And when you use this constraint here, which is now guaranteed to be consistent with supersymmetry transformation, the solution is a simple expansion in theta. So again, very roughly speaking, this d bar operator is the theta bar derivative. So this basically says that phi doesn't depend on theta bar, depends only on theta, except that the spatial derivative piece would dictate that the theta bar appears in this combination called Y. That's a small detail, and you don't need to pay much attention to. But anyway, so you can place this constraint so that you can end up with what we need, namely a combination of the complex scalar field and one left-handed Weyl-Fermion. It turns out that this F comes together with the rest, but it doesn't have any kinetic term, so you can integrate them out right away. So the dynamical degrees of freedom are really complex scalar field and Weyl-Fermion as desired from what I talked about on the previous slide. In the same way, we'd like to describe this combination of the gauge boson and gaugino. So if you take some real function of x theta and theta bar and allow for generic expansion, you have many, many different components. But remember, theta and theta bar are Grassmann odd. So if you take square of theta 1, that's identically 0. So the only way you can square theta is to use theta 1 and theta 2, not theta 1 squared or theta 2 squared. So it stops there. And same with theta bar, so expansion stops at second power. So the highest power in theta and theta bar would be this term called D term, has two powers of theta 1, and the power of theta 1, theta 2, theta bar 1 dot, and theta bar 2 dot. And there are no other terms you can write beyond this power. So it actually stops. But still, we seem to have many different components. It turns out that you can introduce a gauge transformation on this superfield V that would allow you to eliminate these components. Then you are left with one field which looks like a vector boson, and that's a gauge field. And this lambda lambda bar are the gaugino fields. So this is a Weyl-Fermion, this is a CPT conjugate. And D, once again, has no kinetic term, so you can integrate them out. So now you have a theory which has this real vector superfield, which contains the gauge boson and gaugino in it. So that is the particular gauge called Vesumino gauge, according to our late Bruno Zumino. And that's the way you can introduce a gauge multiplet in supersymmetry. And of course, for gauge theory, you need to write down the field strength, which is manifestly gauge invariant or covariant if you go to non-abelian. And you can define it this way, and it contains gaugino field and indeed the field strength. So this actually is a gauge invariant operator for a U1 gauge theory. If you go to non-abelian, things get a little bit more complicated because you have to pay attention to the ordering between V now as a matrix and B as a matrix over here. Gauge transformation is done by this Carrier superfield parameter lambda, but you can see that this field strength multiplet is indeed covariant, just like the field strengths in non-abelian gauge theory we know very well. And now that you have these ingredients, namely fields, you need to combine them together to write down a Lagrangian. And as you can easily imagine, the Lagrangian should be integrated over superspace now, not just over X, but also over theta and theta bar. And when you integrate over theta and theta bar, there are two ways you can actually write down an invariant. One way makes sense. So in addition to four-dimensional space-time integral over X, you integrate over 2 theta and 2 theta bar for this combination of this Carrier superfield. And if you just work out, you can get the usual kinetic term for the complex scalar field with the correct covariant derivative for the gauge field. You get the usual kinetic term for the Y fermion, again with the correct fields, the covariant derivative, including gauge field. And F, I told you, doesn't have a kinetic term. You can integrate them out. And there's other terms you have to pay attention to, which comes with a D. Again, you need to integrate that out. And you find a new Feynman rule here, and which is a superpartner of the normal gauge interaction. So the matter field fermion can emit a gaugino and turn it into matter field scalar. And I show you a picture of that on the next slide. But there's another term you can write, which is kind of strange. You integrate only over half of the superspace, only over theta, but not theta bar. But if this integrand depends only on phi, but not phi star, because phi is meant to be annihilated by acting d bar on it, that was a constraint, you can show the integrating over only the half of the superspace is the way you write down the Lagrangian. Because theta bar integral is basically the same thing as theta bar derivative, and that will make this vanish, so you don't get anything. So you need to stick with only half of the superspace to write down your integral. And if you expand this out, you get these terms, and this part ends up being the familiar Yukawa interaction. And there's also a gauge kinetic term, which turns out to be also integrated only over the half of the superspace. But by writing this out, you get the usual gauge Yang-Mills Lagrangian, the Lagrangian for the gaugino, which is the adjoint Y fermion, and D doesn't have a kinetic term. And if you integrate over D together with this term over here, you get the square of this thing by completing the square. That's a potential called D-term potential, which combines together scalar fields to interact in the phi to the fourth theory, but its coupling is dictated by the gauge coupling. And W is an arbitrary holomorphic function of phi, namely function that depends on phi but not phi star, and comes with F here. So when you integrate over F using this quadratic term, again completing the square, you get this thing squared. So that will give you an arbitrary phi to the 4 potential, if you like. So this is the summary. So this is the way supersymmetry theory looks like. You have the usual kinetic terms. You have the usual kinetic terms, both gauge force, gauge boson, and gaugino. And there's some arbitrary function you can introduce called superpotential. And using the superpotential, you can write down a scalar potential. So in some sense, superpotential is a generating function of the scalar potential. And also there's the potential coming from this gauge interaction called D term. And in the end, that's all you need to know. And so there are several new Feynman rules in supersymmetric gauge theories. I already mentioned this. So as a partner of the normal gauge interaction of fermion emitting a gauge boson, the fermion can emit a gauge GNO and turn it into scalar. And also this Deaton potential I mentioned on previous slide is the the 4-point interaction among scalar fields, but its coupling is dictated by the gauge coupling because this is meant to be in the same partner as the ordinary gauge interaction. And also for this arbitrary Yukawa coupling in the superpotential, the same coupling appears in many different ways of the permutation among which field you take as scalar versus fermion. And there's also associated the pi to the fourth interaction whose coupling is dictated to be Yukawa squared. And this relationship among the sides of the couplings is what guarantees the symmetry as supersymmetry. Now, a little more subtle aspect of supersymmetric gauge theories is there's something called non-renormalization theorem, which says the superpotential, written as this chiral integral, is never renormalized at any orders in perturbation theory. Beta function looks familiar. The piece coming from gauge piece and piece coming from the matter fields, and they subtract against each other. And when this is positive, the theory is asymptotically free. There is a wave function normalization for the matter fields, just like in the ordinary non-supersymmetric gauge theory. There is also one loop beta function to the gauge coupling, but not beyond. This is it. And this piece, as I told you already, is never renormalized at any orders in perturbation theory. But now connect this Lagrangian, which is written in the sense of the Wilsonian action, needs to be connected to what we normally use in perturbation theory. And that connection is also a little subtle because when you take this Lagrangian at the low energy scale after running, you have to make sure that all the fields are canonically normalized. And in supersymmetry, there are anomalies associated with changing the normalization of the fields. So if you change the normalization of the matter field, it turns out the path integral measure is anomalous and ends up giving a correction, which appears together with the gauge coupling constant. And after that, you also need to make sure that gauge field has canonical normalization. So you need to change the normalization of the gauge multiplet. And that also turns out to be anomalous. That ends up correcting the definition of the gauge coupling constant. So as a result, you get these additional pieces going into the definition of the gauge coupling constant. And after changing the normalization of gauge multiplet, you also get this additional piece. And it turns out that this actually defines the exact beta function at any orders in perturbation theory. And by taking this normalization, you are now in the normalization, which is consistent with the standard perturbation theory. And so that you can compare your calculations with the standard, say, MS bar calculations you have studied in QFT. And in that kind of calculation, there are beta functions beyond two loops, but they all come from this wave function normalization of the matter fields and this normalization for the gauge fields. So they are all captured in this single formula. So that kind of thing is one concept on supersymmetry. And you already see the sign that this symmetry is very powerful to constrain the behavior theory, even at the quantum levels. So that's a brief the review of supersymmetric gauge theories. So let me again pause here to see if you have any questions. And next thing is to talk about supersymmetry breaking. Again, this part is rather technical. So if you're not interested, you don't need to pay too much attention. And you can always look at the slides and watch the video later if you want to recover some of that. But for the rest of the discussion, you don't need too much of it. Okay, so then I think I can hope I can go on. So now I need to tell you how I introduce small supersymmetry breaking so that we stay near SUSY, but nonetheless, it's non-SUSY anymore. And that is a scheme I proposed some time ago in competition with with Randall and Raman syndrome, and it's collectively called anomaly-mediated supersymmetry breaking. So we have a particular needs here. So we'd like to connect supersymmetric gauge theory, which have been solved exactly by Seiberg, to non-supersymmetric gauge theories, which means that there are some particles we don't want. So every fermion quarks in supersymmetry are partnered with the scalar partners, quarks, and we don't need them. We need to make them massive. Every gauge boson is partnered with the gauginos. Again, we don't need them in non-supersymmetric gauge theory. We need to make them massive. So we need to find a scheme to make gauginos and quarks massive and heavy. So we need both of these. But at the same time, we have this need to deal with non-perturbative effects like composite objects such as mesons and baryons. So we need to make sure that even when theory becomes non-perturbative, we have a good theoretical control on how exactly supersymmetry breaking would appear in your Lagrangian. And in particular, we, for example, need to know signs of mass squared for various scalar degrees of freedom like mesons to see if they condense or not. And so we need to have a good control to be able to compute signs, for example. And it turns out that there's only two known ways in the literature to do so. One of them is anomaly-mediated supersymmetry breaking. Another one is called UNRD term. I don't get into that because this UNRD term can generate squark mass, but not gaugino mass. But with the anomaly mediation, you get both of them. So this is just a minimal choice you can make to satisfy your needs. Namely, one, you make gaugino and squarks massive, and second, you retain theoretical control. So that's why I went for this anomaly mediation. And how do you maintain external the theoretical control is something you have seen already based on external symmetry. So if you have some external symmetry, like chiral symmetry in QCD, what we know in the QCD Lagrangian is that the massless theory has this chiral symmetry. You introduce quark mass, which breaks chiral symmetry, but we talked about this spurion idea by pretending that quark mass transforms under the chiral symmetry. You can show how these quark mass terms can be considered to be invariant. So the chiral symmetry is still there. And knowing that, you switch over to chiral Lagrangian together with this chiral field U, the exponential pion. You know exactly how the quark mass would enter the low energy chiral Lagrangian by making sure that this is actually invariant, assuming again M transforms under the chiral symmetry. So in this case, having an external symmetry to the theory, namely chiral symmetry, dictates how low energy theory can contain the symmetry breaking in it. And so that's the way we have been using this idea that external symmetry is useful to have a theoretical control on how breaking parameter can enter even in non-perturbative physics. And this way, we learned in class, and you have done even homework of it, that pion mass squared goes linearly with quark mass, which is very counterintuitive, right? Because if you make the constituent of pion massive, you would normally think the pion mass linearly goes with the quark masses, but it actually goes like a square root of it. But we feel confident about this behavior of square root because that's a consequence of the symmetry we know we made sure of. So this is the way you can get even some non-trivial, non-intuitive results, but you can believe in it because the symmetry dictates how symmetry breaking can enter even in non-perturbative fashion. And same thing applies when you put QCD on a curved background. And so you can couple QCD to the curved space-time. But again, you don't need to do anything to know how the curved spacetime will appear in chiral Lagrangian 2, because that behavior is completely dictated by the general coordinate invariance. So that's just yet another example. So we are trying to come up with a scheme where how you break supersymmetry is completely dictated by the external symmetry. And that external symmetry turns out to be the supergravity. And once you introduce gravity, things tend to become more complicated. But this is just a supersymmetric version of gravity we know. So if you combine supersymmetry and general relativity, there's a unique theory, which is called supergravity. And the only assumption you make is that the way you introduce supersymmetry breaking effect in your gauge theory is through supergravity as dictated by the supersymmetric general coordinate invariance. So you know exactly how that would enter your theory. And to guarantee that is the only source of supersymmetry, you don't want to have direct interactions between whatever breaks supersymmetry to your gauge theory. So you need to sequester them. But once you do so, the supergravity invariance completely dictates how supersymmetry breaking would appear in your theory, and that's how you can maintain theoretical control. Now, when I was working on this anomaly-mediated supersymmetry breaking, I was really saved by time zones around the world. So I was at CERN in summer 1998. I started to work with Gian Giudice, Riccardo Rattazzi, Marcus Rudi. They were all together at CERN that summer. And we basically finished discussions and finished the work. We have a half-finished draft already. But when we left back to our home institutions, then, we became busy with teaching and committees. And so the draft was sort of remaining half finished. So that is how it was in the fall semester. But one day I was checking the archive at my home in Berkeley and found a paper from Lisa Randower and Ron Sundrum, which did exactly the same thing. And so I freaked out. Oh, we got scooped. So I emailed my friends. And then, so it was late in the evening for me in California time, but that was a time when people in Europe started coming to work in the morning. So Jan and Ricardo told me, okay, it's late for you. You should go to bed. But we are now waking up and going to the office. We have a half-finished draft. So let us work on this to finish it as quickly as we can. You go to sleep, we work. So they got set to work on that draft. And when they go to dinner that day, they handed that over to Marcus, who was in Maryland on East Coast at that time. And he kept working on the finishing of the draft. And in the end, it came back to me. And then I submitted it before the cutoff so that our paper appeared only with 1 day of difference from Lisa Randall and Sundrum. And that convinced everybody in the world that what we have done is an independent work, not just stealing the paper that appeared already in your archive. And without this 1 day, I would have earned no more than 1,500 citations on this paper. So the time zone really helped that day. So I normally hate time differences. I'm right now in Japan and I'm jet lagged, but this is the 1 day when I appreciated time differences. And the way it works is the following. So we basically introduce a space-time background, but in superspace. So space-time is still Minkowski flat space-time, but in the theta direction, it's curved. And so that can be captured basically by the analog of square root minus g we do in the general relativity. And this curved space in theta direction is captured by this single parameter m, which is the size of supersymmetry breaking of mass dimension 1. So it has the dimension of energy scale in it. So this is the space-time curved in theta direction. And this is basically square root minus g that goes into the Lagrangian. And then everything else is dictated by this general coordinate invariance in supersymmetry. And all effects of supersymmetry breaking then is encoded in power series in this E parameter. Okay, so then when this SW superpotential is phi cube, you can see that you can rescale phi by E to absorb it completely. And so there's no supersymmetry breaking at the tree level at the end of the day. But when the theory contains some mass parameter in it, like a mass of the matter field, this is not cubic power. That gives you this extra power of E in the end. And E contains theta squared m in it. And theta squared can be integrated over theta to give you 1. So you find m, little m, phi squared. And that is a mass term actually that breaks supersymmetry. Generically, at a tree level, you get this contribution to the potential. But it turns out the theory is a little bit more subtle because when you do QFT computations at the loop level, you have to regulate your theory, like Pauli-Vilas regulator. And Pauli-Vilas is the opposite status field with heavy mass M. But as we just talked about, heavy mass would acquire supersymmetry breaking in it. So in 1 over g squared, which now has theta squared in it, if you do an expansion with it, you get the derivative of 1 of g squared. That's nothing but a beta function. So what you would predict is that the gaugino now acquires a mass proportional to the beta function. And so this is a definite prediction out of this scheme, namely that supersymmetry breaking appears only in relationship with the energy scale. And the way gauge coupling acquires energy scale is through running. And that running ends up giving you the gaugino mass. And also the gaugino mass depends only on the particle content at the energy scale of your interest. So you have a unique prediction without knowing what's going on at high energies in your theory. And that's the behavior called UV insensitivity. And that's why we can actually use this to work out the consequence of SUSY breaking in the low energy limit among composite objects like mesons and baryons. And that sounds too good to be true, but when you actually integrate out some heavy matter particles, then you always find a consequence which do not include any impact of the massive particles at the end of the day, hence UV insensitive. For example, when you look at the theory which contains heavy massive particle in it, and then the beta function includes that at high energies. But when you go below the threshold, beta function doesn't include the heavy particle anymore. So beta function jumps. And it turns out that when you integrate out this heavy particle, and you need to compute this one loop diagram as a threshold correction to the mass of the gaugino, and these threshold corrections end up precisely canceling the contribution to the beta function of this massive particle. So in the low energy, then you end being the correct formula with the beta function that does not include this massive particle anymore. And same thing also applies to a scalar masses, which again comes from the impact of the running. Therefore, it's proportional to enormous dimension in the wave function organization. And again, you can show that heavy particles would completely decouple from the prediction in the low energy theory, thanks to these threshold corrections, which happen to be two loop, but you can actually work them out. So at the end of the day, this is the general formula. You have this tree-level expression for the potential, if you have a superpotential with dimension 4 parameter. And you also have these the expressions from the loop level on scalar mass and gaugino masses. And everything's determined only by physics at the energy scale of your interest. And that's why this theory is predictive and maintains a good theoretical control. This scheme of supersymmetry breaking ended up being described in the QFT textbook by Steven Weinberg in his third volume, and I feel very honored that he actually acknowledged my contribution in his preface. So now we are ready, and I'm afraid I'm running out of time, so let me just hedge on and apply everything I talked about to QCD now. So when number of flavors is less than number of colors, I told you that theory doesn't have any ground state in a spherical Cal limit of supersymmetry. So the superpotential is written by the composite object of meson operator, and it's inverse with the meson in downstairs, and hence runaway behavior. So potential, if you actually work this out from the superpotential, looks like this. And that this red curve over here. And so that's why there's no ground state. The squawks end up being driven to all the way to infinity with no stable minimum anywhere, and hence runaway behavior. But now that this superpotential, which is non-perturbative, includes this dynamical scale of the gauge theory, lambda, it's dimension 4, then you have this tree-level piece coming from the anomaly mediation, supersymmetry breaking. And then you find this blue potential, which now has a well-defined minimum. And once you solve for the minimum, which you can do on a piece of paper if you like, you'll find this meson to acquire an expectation value with a complicated combination of the dynamical scale and SUSY breaking. But it's proportional to delta ij, which means that I index that transforms under SUNF left, J index that transforms under SUNF right, is now broken to diagonal subgroup, which makes this delta ij invariant. And so you have now derived chiral symmetry breaking just by minimizing the scalar potential. And when you go to the low energy limit, you need to integrate out everything that has a mass, like the superpartner of the meson called mesino. That's the fermion. And when you integrate over the fermion loop has an anomaly, and that exactly reproduces the Wessel-Witten term we talked about in class. And you can derive chiral Lagrangian now from the first principle. Once that you know that meson has an expectation value, and because meson is the product of Q and Q twiddle, then you have the expectation value for Q and Q twiddle. And just like what you do in the standard model, you look at the fluctuations around this minimum. In this case, given by a matrix C, that's a pion field. And then you just plug in this fluctuation into the kinetic term of Q and Q twiddle, and there just pops out the chiral Lagrangian. And that gives you a prediction on what f pi squared, pion decay constant, is, which is an intrinsically non-perturbative object, but you can predict that. And if you do a careful translation after talking about this rescaling anomaly, you can demonstrate that f pi squared is indeed order NC. And some people back in 90s actually didn't understand this the translation very well. Just by staring at this formula, it doesn't look like order NC, and said, well, there must be phase transition as you make SUSY breaking larger, but that was wrong. So right now, this is the first sign that there doesn't seem to be phase transition from near SUSY limit to non-SUSY limit because of the correct behavior of pion decay constant on number of colors. And you can also compute the mass of the eta prime now that you have the scalar potential. So you know this story already. There's an anomaly, so that you expect the eta prime to acquire mass. And here we go. This is the prediction on what eta prime mass should be. And X is the ratio of NF over NC. And in the large NC limit, this becomes a linear in X, NF over NC. And that is exactly the right behavior as Witten told us a long time ago. And he came up with this formula, which is a very strange formula, that F pi and M eta is what you compute in theory with massless quarks. This topological susceptibility is defined in a theory without massless quark. This is the pure Yang-Mills theory, because when you have massless quarks, the theta can be rotated away by chiral transformation, as we talked about in class. So this can be computed only in the theory without massless quarks. So you're comparing two different theories. But in our technique, you can work out both of them and take the large NC limit, and they are exactly, indeed, agreeing with this formula. And you can also see the deviation from this formula when NC is not infinite, but finite, and that captures this additional 1 over NC separate pieces in eta prime, the propagation. And so you can get even more information than Witten's formula with a finite NC and finite NF. I already told you that you can actually work out this fermion bilinear condensate and gauge boson condensate. And when you start making the SUSY breaking scale higher, this gray area, I lose my theoretical control. I can't compute things anymore. When M is above lambda QCD, I can first integrate out quarks and gauginos. You have now the QCD as a non-supersymmetric theory. And you can only do dimensional estimate on how the condensates would behave in that regime. But point here is that, they seem to go continuously connected from small m to large m. So once again, I take this as a evidence that the small SUSY breaking and large SUSY breaking are crossover, connected continuously without phase transition. And you can even study the behavior of f pi squared when nf is also as large as nc, which correspond to these diagrams, which are not captured in large NC limit. And that is actually a new prediction nobody was able to work out before. Now that our meson is a complex scalar field because it's part of the supermultiplet, in addition to massless pions, you also have CP even scalar fields. And here's a spectrum with no quark mass introduced. And once you introduce the quark mass, we know that pions and kaons acquire mass squared proportional to quark mass. So they become heavier as square root of the quark masses. And pion is the lightest. Kaon is the next because of the strange quark in it. Eta is the heaviest among the Goldstone bosons. And eta prime already acquired a mass from the anomaly. So the pion mass squared goes linearly with quark masses. But the question is that now there are these experimentally established 0+ scalar hadrons, F naught 500, K naught plus 700, A naught 980, and F naught 980. And these states used to be very controversial because they are incredibly wide. They showed up as a resonance in pi-pi scattering. But instead of the fixed target experiment people used to do a lot in 60s and beyond, now we can produce these states top down from, for example, J psi decay. Then you clearly see the resonant peak in spin zero channel in pi plus pi minus spectrum. So this is the way now experiments are much cleaner in E plus E minus experiments to produce J psi and really clearly identify the pi pi resonance in it. So that's how we know this mass spectrum. Now, you can ask the question if they can be understood as a QQ bar meson state, and that actually turns out to be no. First of all, this isotriplet doesn't contain strange quark in it, if you think that's a QQ bar state, but it's a lot heavier than the state that contains strange quark in it. That is difficult to understand. Also, that if you would like to get the 0+ state as a QQ bar bound state, the orbital angular momentum must be 1. And then you're talking about spin of quark anti-quark combining to spin 1, orbital angular momentum 1, that gives you total spin of 0. But then that should be accompanied by also 1 + 1 giving you 0, 1, and 2 of total spins. And we don't seem to see these states either. So to make everything consistent, these states cannot be understood as a QQ bar state, but rather tetraquark state or meson-meson molecule. And indeed, if you think of the meson-meson molecule, the octet times octet contains octet in it, and that is supposed to be these 0+ states. And the question is, how do their mass spectrum behaves? What you see here is the spectrum is upside down. You start with some heavy mass, and this mass squared is pushed down, proportional to quark masses. So instead of m pi squared going up linearly with the quark masses, these scalar masses are pushed down with negative C prime together with quark masses. And using our technique, we found C prime to be indeed negative and about -2. And if you use these numbers, you really do reproduce this spectrum as observed by data. So this seems to be really working. Now I'm going to skip some slides because I'm running out of time now and not talk about larger number of flavors, but mention something else. Namely that when you go to use SUN gauge theories, the Wilson loop, which is supposed to be the autoparameter confinement, can be always screened by fundamental quarks running inside the loop. So there's actually no rigorous definition of the area law of the Wilson loop and hence confinement. But if you go to SO and C gauge theory with quarks in vector representation, you cannot screen Z2 charge of the spinor representation. And now you have the rigorous definition of confinement. So it turns out that as Intrigator and Cyber worked out, for SO and C gauge theory, when NF is NC-2, you can find the Coulomb phase. And in this Coulomb phase, you can identify magnetic monopoles. And these magnetic monopoles actually become massless at 2 points on the space of the ground state. And this point gives you both the meson web and the monopole web once you actually introduce supersymmetry breaking. And this is the global minimum. Namely that if you take this theory, you find that the monopole and the meson acquire expectation values at the same time, namely causing confinement and chiral symmetry breaking at the same time. So this is the way you can really show the confinement happening in the theory where you can rigorously define confinement to begin with. Okay, so now I just skip over many things about chiral gauge theories, but it is a fact that you can really work also dynamics of chiral symmetry, the gauge theory, non-perturbatively. And this is the work I have done with many students and here. And so in many cases, you end up finding the symmetry breaking patterns that are very different from what people speculated based on this tumbling hypothesis we talked about in class. And right now, the verdict is still not there. So we don't know which one is right, but at least here, I can claim that this is an exact result, including non-perturbative effects, as long as supersymmetry breaking is small compared to the dynamical scale of the theory. Okay, so that wraps things up. And I post these slides on the B courses so you can look at it later. But here's a summary. So if you combine supersymmetry with this particular scheme of supersymmetry breaking, that will help us understand quantum dynamics. You first go to SUSY limit, that's spherical cow, you break it a little bit, then you can start picking up all the right features of the non-perturbative impact of the dynamics on the gauge theory. And end results end up being very much consistent with what we expected, what QCD should be doing. And there's no obvious signs of phase transition to go back to the real cow as SUSY breaking is increased. And so that's the way we think that there's a crossover. And you can apply this also to chiral gauge theories, and in principle, to lower dimensional field theories, which may be relevant to the quantum matter physics as well. And the reason I actually started doing this is to actually use this technique now applied to the model building of strongly coupled dark sector, understanding dark matter, axion, potentially composite inflaton and dark energy. So this is the way I'd like to actually use this, the principle, to get better insight to what the non-perturbative physics might do. Okay, so sorry, this is the end of the time, and the Sarah already logged off, but I can take some questions if you have any. No questions? Last opportunity. Okay, then if there is any, then this is the end of the class. And I hope you can turn the video on so that I can say bye to all of you. Yeah, just the three of you here, but I'd like to do that. Thanks for joining me, and have a good holidays.
Thank you.
Thank you.
Bye.
Thank you.